Let's go ahead and look at another example. Let's look at the limit as x approaches 0 of tangent of x over x. Always put parentheses around the arguments of your trig function, and of course do not be tempted to cancel here because I cannot cancel within the argument of my trig function. So we'll go ahead and plug in directly. I get tangent of 0 over 0. 0 over 0 is indeterminate. Indeterminate means to do more work. Well, what more work could we do? Well, we could look at this graphically. In Maple, we could produce a table numerically and plug in values for our radians as we approach 0 from the right and the left, or maybe we could use one of these theorems that involves trig functions. First of all, tangent of x is equal to the sine of x over the cosine of x, and of course I have this 1 over x running around here as well. If we rewrite this, you'll see something familiar. I have sine of x over x times 1 over cosine of x. Now remember, the limit of a product is the product of the limits, so I can rewrite this in two steps. I can take the limit of each factor of that product. So from theorem 2, this is equal to 1 from theorem 2. I didn't have to compensate with anything missing. And here I can plug in just by substitution. By substitution, I just go ahead and plug in that 0, and I get 1 over the cosine of 0. The cosine of 0 is 1, so I just get 1 here. So combining those, I get 1 times 1, which is 1. You can verify this graphically using Maple as well, but this is a pretty straightforward problem as soon as I try and rewrite this to get that look at it. Our next one we want to look at is the limit as x approaches pi over 2. So far everything's been a nice quadrantial angle. And I'm left with 1 minus cosine of x over x. Now this looks pretty familiar. You know, if you run up at this theorem, 1 minus cosine of x over x, this looks very familiar to this piece right here. However, what's different is this. In this case, theta, my argument, is approaching 0. So that's really important to note. Here, that argument is approaching 0. However, in our problem down here, the argument is approaching pi over 2, so I can't use that theorem. First thing we should always try is to just plug directly in. The cosine of pi over 2, of course, from your unit circle is 0, with pi over 2, so I have 1 divided by pi over 2. When you divide by a fraction, you multiply by the reciprocal, and I'm left with 2 over pi for this one. I could plug directly into this. I didn't have to actually go through and apply a theorem or rewrite. I could just plug directly in. So again, things to be careful of here are make sure the argument matches the theorem. Our next one, let's look at the limit as x approaches 0 of the cosine of x minus cosine squared of x all over x. Again, first thing we do is plug directly in. The cosine of 0 is 0. The cosine of 0 is 0. 0 squared is 0. All over 0, so I have 0 over 0, which is indeterminate, and indeterminate means to do more work. Well, the more work we can do here, I don't really see anything right off the bat. Let's go ahead and look at this algebraically. I do see a cosine that's common to each factor in the numerator, so I could factor out a cosine. And now I'm seeing something that looks kind of familiar. 1 minus cosine of x over x. So I can look at this factor and rewrite. So let's look at the limit as x approaches 0, and I'm going to pull this apart very strategically because I want to be able to take the limit of this first piece using that theorem. Okay, so I have two limits being multiplied together. This one, the argument matches my theorem 2. The arguments match my theorem 2. So let's go ahead and look it up and see what that is. Remember the graph, that limit should equal 0. Remember the graph, so this limit equals 0 as we approach 0. So this is equal to 0 by theorem 2. This one I just plug in. Substitution is the method I use here. So by plugging in, I have the cosine of 0, which of course is 1. So I have 0 times 1, which is 0. So this indeterminate form turned into 0. And of course, it's important to note how you got this answer, and so that's why we quote the usage of Theorem 2. Let's look at the limit as x approaches 0 of the sine of 2x, sine of 3x, all over x squared. And again, plug directly in, we get 0 over 0, which is indeterminate. Indeterminate means to do more work. You always have to show this intermediate step. You always have to show plugging in, the results from when you plug in, and the conclusion in this case was to do more work. Well, this is not looking similar to that Theorem 2, but it looks pretty close. So let's see if we can rewrite this one as well. Let's look at the limit as x approaches 0 of the sine of 2x over x times the limit as x approaches 0 of the sine of 3x over x. This is very similar to one we just did up above. This would work great if only this was a 2. And of course, if you divide by 2, you have to multiply by 2 as well. And I'll just go ahead and pull that out in front of the limit. And this one would work great as well if I had a 3 in the denominator. So if I have to divide by 3, you have to compensate with multiplying by 3 as well. So this piece equals 1 by Theorem 2. This piece equals 1 by Theorem 2. So really what I'm left with here is 2 times 1, 2 I'm dragging along, 1 is from Theorem 2, times, because we're multiplying here, 3 times 1. So in this particular case, when I multiply everything out, I have 6 for my limit. The last problem that we're going to be looking at is the limit as x approaches pi over 4 of x over sine of 11x. 11x, not 11 pi. Well, of course, we plug directly in, so let's see what we get back out of this. Plugging in pi over 4 into the numerator, I get pi over 4. Now into the denominator, I get sine of 11 pi over 4. So let's look at that one a little bit. Let's see where that is even. Well, if we look at our unit circle, or our quadrantial system here, this would be 1 pi over 4. Here we are at 2 pi over 4. Here's 3 pi over 4. I'm sorry, this is pi over 4. This is 2 pi over 4. Here's 3 pi over 4. Here's 4 pi over 4. 5 pi over 4. 6 pi over 4 would be this quadrantial angle. Here's 7 pi over 4. And of course, to come right back to our start would be 8 pi over 4. And then we just keep counting. 9 pi over 4. Okay, and then 11 pi over 4 would put me right here. These angles are called coterminal, meaning one rotates more than the other, but they end up in the same spot. So first of all, I want to note that this is in the second quadrant. So 11 pi over 4 is the second quadrant angle. And of course, in the second quadrant, sine is positive. And since it's a multiple of pi over 4, I get square root of 2 over 2 here. Now my numerator is just good old pi over 4. This is not indeterminate. This is not undefined. So I can just work with this. Now remember, when you divide by a fraction, you multiply by the reciprocal. And I do see some canceling that can occur here. So it looks like I'm left with pi in my numerator, and in my denominator I have 2 root 2. Now if you wanted to, you could rationalize. I think this is a great solution. But if you wanted to, you could rationalize by multiplying top and bottom by root 2. And of course, square root of 2 times 2 is 2, so I'm left with 2 times 2 is 4 here. And here's my solution. So again, knowing your unit circle is crucial here. These will show up a lot on exams and quizzes, and if you don't know your unit circle, you're kind of stuck.